Hi, welcome to the Lattice Drive presentation, Paving the Road to the Future. I'm Mark Hoops, Director of Industrial and Automotive at Lattice. Been at Lattice for a little over 4 years. Today we're going to give a background of Lattice in automotive, some of our automotive devices, and then we'll get into the Lattice Drive software stack, features and functions, and go through those details. So in automotive, FPGAs are used literally all over the car in very different sections. Things like an infotainment for defog, image signal processing, display bridging, and ADAS subsystems for sensor bridging and applications with radar or cameras. In hybrid electric vehicles and inverters and charging circuitry and security, and also in cabin AI or in driver monitoring types of applications. And overall in the industry, the automotive industry is going through its largest change in the history. There's a lot more electronic content in the vehicles. They have requirements to scale solutions all the way across different model lines, so they need a lot of flexibility in the systems. And they also need to have low latency, deterministic processing of data. So from a timing standpoint, things need to be very low latency to control and manage a car at speed. And what we're seeing is there's a dramatic increase in the usage of displays, sensors, and cameras. So each one of those presents an additional opportunity for FPGAs, increasing the number of FPGAs per vehicle. And there's a wide range of different types of pricing depending on what the application is. Overall, Lattice has a wide variety of automotive products. We have general purpose FPGAs with some high-speed SerDes up to 8.1 gigabit, up to 100K logic cells, and small packages, low power devices. We also have FPGAs that are optimized for video connectivity, the Crosslink family and Crosslink NX that have things like hardened MIPI D5s. And then we also have a control and security portfolio meant for providing platform management and security kinds of applications. So these are all the different types of products available for automotive applications. In addition to providing devices, we also provide solutions or stacks in order to accelerate adoption of FPGAs in different applications. So we started a couple years ago with a Sense AI stack for implementing low power edge AI applications. We have Lattice mVision for cameras and video and vision systems. Sentry is our cyber resilient stack. And we have one for industrial automation, one for ORAN. And our most recent stack that we'll be talking about today is Lattice Drive, enabling adaptable automotive designs. And one of the things that we've seen that's been very encouraging is that through adoption of the stacks, we're seeing that customers can accelerate their time to market. So reduces the time from when they start a design to when they're ready to deploy the product. So that helps them get to market faster and Lattice as well. And we're also seeing a much higher attach rate in terms of the number of customers that are adopting our stack. So it's been a great strategy and it's working very well for the customers and for Lattice. Switching now to the Lattice Drive stack. What you see highlighted in green, infotainment, display bridging, and processing is the focus of our first release for Lattice Drive. We also have other areas that we'll address in the future, talk about a little bit more. Functional safety, certified design software is something that we offer across the board. Um, enabling low power driver monitoring, vehicle monitoring is another area in the future we can address, and ADAS sensor bridging and processing as well. Now, if you look at our stack, it's basically we have 5 layers. Starting at the bottom, the lowest layer is hardware kits that are designed to make it easier to develop and prototype the solutions for the application. So in this case, we have a modular FMC card with some daughter cards that enables DisplayPort transmit, receive, or embedded DisplayPort. And this is all focused on, enabling bridging for displays. And we have a Certus Pro NX PCI bridge card, which is the main card that is running the algorithms. And we changed the IOs with the FMC card. On the IP core side, we have DisplayPort receive, transmit, and video scalers. Those are all included in the first release of Drive. Then we'll be having some additions to that where we enhance the DisplayPort offering in the future and offer other types of cores such as image enhancement or variations and updates to local dimming kind of algorithms. In the middle are software tools. We have industry standard Radiant tools for our Nexus family products, primarily. In Propel, we have to enable embedded system design with an integrated soft core RISC-V CPU. Moving up one level, we have reference designs and demos. And in this release, we have a DisplayPort with a video scaler reference design. And then we also have embedded DisplayPort with video scaling and local dimming as well. And then in the future, we will be offering additional types of functions, integrating more and more different capabilities into the stack, such as video frame buffer, other types of image enhancement, and things like that. And last but not least, on the very top, we have custom design services. And in some cases, these can be offered by Lattice, such as local dimming or driver and in-cabin monitoring. And some could be also offered by partners, third-party partners that we're working with. That could also be things like automotive bridging and networking. So that's a view of some of the first release features and functions and some of the future types of things that we're looking at offering down the line for Lattice Drive. I'm focusing a little bit more on the first release and the examples that we're enabling through this release. You can see here a typical interior cockpit. Modern vehicles are including more and more displays and more cameras in the vehicle. So you'll have, in general, you'll have what's called an infotainment domain controller. It's the main processing unit that monitors and controls all the displays in there. And you might have a heads-up display. You'll have where the speedometer is typically, and an infotainment screen, or also a screen maybe for other types of controls. And last but not least, things like electronic mirrors are starting to replace standard mirrors so that you can have a camera in there that shows you a wide-angle view in a display, and you can see more clearly if you have something in your blind spot or something like that. So we're focused a lot on display connectivity, where we enable the main processor to connect to more and more different types of displays. So the FPGA is doing bridging there. And we can support DisplayPort at HBR3 up to 8.1 gigabits per second, which is enables you to get higher resolution, higher frame rates, or more displays on the same connectivity. We also are enabling sensor aggregation to be able to connect multiple different types of sensors together. And then the ability to not only bridge it into the processor, but also do some pre-processing or co-processing in order to offload the main CPU. Switching now into local dimming. Here's a diagram basically of how things are split up in terms of signal processing. So on the left-hand side, starting there, that would be your main CPU, your main processor, and it would feed data, video data, over OpenLDI or some other interface. In this case, we're using OpenLDI as an example, into something that's called a timing controller, TCON. And that enables the display to be managed in terms of showing the video or showing the content, in this case, the speedometer, on the actual LCD display itself. And then separately, in another device, you've got a LED control circuit that takes the video and manages the backlight. And so on the bottom there is an LED-based backlight. So it's basically a large array of many, many LEDs that provides the backlighting for the LCD display. And the reason for having many LEDs in different zones is to be able to enable local contrast optimization across the screen. So where something's meant to be bright white, you'll have plenty of light behind it. And where something's meant to be dark, you can turn down the LEDs so that you get a much better contrast ratio and better visibility. That's extremely important in automotive because you have very difficult lighting conditions. If it's at night, you don't want things maybe too bright. You want to be able to adapt it to the low light. But if the sun is shining on the screen or something like that, or maybe some headlights or something, then you need to have a better quality panel. And so local dimming is used to optimize that. What we're doing in Lattice Drive is, for one thing, we can replace the driver for the LCD screen, and we can do different functions like just bridging different types of interfaces. Maybe you have it, in this case, you have a panel that accepts an embedded DisplayPort signal, but you have a processor that does not have that output. So we'll do the translation there, as well as passing on the video. And then we can also send signals down to the LED controller and have the LED controller control the backlight. That's one example use case. We also are able to take the algorithms that are put into the LED controller and integrate them into the FPGA. So now you don't need two chips. You can just have a single FPGA that is managing both the LCD panel itself and the backlight in order to optimize the video. So when you put them together, you'll get an optimized display, and you have a small low power single solution that gives you the optimal video capability, but also flexibility on what CPU you use and what panel you use, because the FPGA can bridge between them for any type of interface. And we can not just do the local dimming solution. So we can do things like scaling, we can do rotation, all kinds of other different types of image processing functions can be done in the FPGA. In addition, we can also enable fail-safe functions in order to be able to ensure that critical data is still displayed. For example, if you have a fault where maybe the content that is coming into the display isn't updating properly, it's stuck somewhere, then what we can do is we can pass on the non-critical information as is, and if it's sort of best effort. But for things that's critical, we can add fail-safe modes to it to ensure that it won't get stuck, and that'll be updated. In this case, you'd want to make sure that the driver can always understand what speed they're going. That's an example. But the odometer doesn't matter, or the media stuff doesn't matter. That can go out and not be a safety feature. Now I'll show a short clip that shows what's going on behind the scenes. So here you can see just a very simple example of a bright white light roaming around the screen, or a bright white square roaming around the screen. And so what you see on the screen is to the left, and the backlight that was moving pattern of LEDs on and off is what you're showing in order to improve the video quality. And here we're looking at a block diagram of one of the demos that we have at the show. In this case, our video source is an external industrial sort of PC, Raspberry Pi essentially. And it's outputting a video stream at 720p resolution. That's brought into our Certus Pro NX FPGA. And the first thing we do is we go into a scaler. So we take it from a 720p resolution up to 4K resolution to improve the quality and make it look good, because we're looking at driving a 4K full array LED panel. At the same time, the signal splits off and goes down to local dimming intellectual property that controls the algorithm via the FALD, which stands for full array local dimming interface, into the LED back panel. So that's going to control all of the LEDs behind it to enhance the picture. And the upscaled image then is output over embedded DisplayPort into the panel. So we're taking sort of a open LDI input, scaling the video up, passing that on through it at 4K, and then enhancing the backlight, all inside Certus Pro NX device. We also have a soft RISC-V processor in there for control functions. Now I'm going to show a little demo of the kit. So here you can see the development board in the bottom of the kit, and on the top is the 4K full LED backlight panel. And here you can see side by side, on the left without the backlight control on, and on the right with the backlight control on, improved colors, improved contrast ratios, and overall makes a big difference in terms of the quality. So kind of summarizing the local dimming solution, you can see the block diagram there on the left. We're showing the video scaling, we're showing local dimming, and we're showing various different interfaces. So benefits of the solution is you can use this with a wide variety of different displays, different interfaces, different number of zones, different resolutions. All those are easily handled by the overall solution. We can also add in other types of IP later on in the future, things like image rotation if need be. And some of the benefits of it is the FPGAs are actually very low power, so it's no thermal issues, and it's well suited for the automotive environment. We also have high performance, higher than a lot of the other options in there, to enable either higher resolution displays or more displays to be used in the vehicle. So that's the introduction to Lattice Drive, and again, the focus is on infotainment, display bridging, and processing initially, but we'll be adding things in the future and releases focusing on things like in-cabin monitoring, vehicle monitoring, and more sensor bridging and processing. Okay, so now we'll switch to some of the questions that folks have from the audience. So I guess the first question is, why are FPGAs used so much in cars? Because aren't they just for prototyping or evaluating? And the answer is that cars are undergoing such changes in the industry that it's really, really hard to develop just the right chip that is going to fit all the needs. And the technology is rapidly changing. The interfaces are changing, the algorithms are changing. And so OEMs need to be able to adapt quickly to add more features and functions. They also need to be able to have sort of a scalable solution that can go from high volume, lower cost cars up to mid-range and all the way up to the premium vehicles, leveraging a common architecture, but with more or less sensors and more or less capabilities per car. So FPGAs give them the ability to adopt newer technology sooner, give them supply chain flexibility, and give them modular architecture that is scalable. Another question is, why is an FPGA good for doing local dimming? Isn't that something that could be done by an ASIC? And the answer is there are ASICs out there that do that, and they do a pretty good job of it. But with an FPGA, we can implement more functions and have more flexibility at the system level for the vendor. So instead of being stuck with whatever the features and functions are that were designed into that one chip, you have much more flexibility. You can change the interfaces, you can change the algorithms, change the number of zones, the resolution, and you can tune them very easily to different types of physical implementations of displays. So it basically gets down to enabling flexibility and adaptability at a solution that the price point is very similar and the power levels are very similar. So you get the benefits and flexibility without paying a significant penalty or anything. Another question is, so this first release is focused on displays and interfacing. What's coming next for Lattice Drive? And there we'll be implementing some of the things where we're in early engagements with customers now. We'll start to bring those into the stack. One of those areas is all around monitoring in the vehicle. So monitoring inside the vehicle, arguably one of the first most important things is to monitor the driver, to assist in keeping the vehicle safe, both for the occupants and for people in the roadways and things like that. And another benefit that we can provide is for external vehicle monitoring. In these cases, what we can do is implement AI in order to understand what's going on outside the vehicle and be able to continuously monitor it at very, very low power. So that's an example of something that we can be bringing forward in the future. And with that, no more questions. So thank you for your time, and please reach out if you have any additional questions later on.